Okay, in part 2, we're going to look at the graph of log functions. Y equals log b x, and kind of makes sense since they're inverses of the exponential function. Then we're going to have the same situation. The graph is going to look a little bit different depending on if the base is greater than 1 or if the base is between 0 and 1. So let's start with some common things between the two graphs. Let's start by looking at the x-intercept. Okay, so the x-intercept, if you remember, that's the point where there's some value of x when y is 0. So at 0, where do we cross the x-axis? Well, put 0 in for y. Function equals 0. What does x equal? Okay, so we do our conversion. Base to the exponent equals the number, but a base to the 0 power always equals 1, so x equals 1. So all graphs, regardless, share the point 1, 0 for the x-axis. So let's go out here. We'll call that 1. How about the y-intercept? Let's see what that looks like. Again, for the y-intercept, if I'm going to cross the y-axis, x would be 0 at that point. Okay, so if x is 0, what does y equal? Put 0 in for x. Y equals log base b of 0. Convert. So we have a number 0 equals base to the y. But the problem here is the base is always greater than 0. So if I raise a number to a power, it can never equal 0. So what happens here? Since we can never equal anything on the y-axis, becomes an the y-intercept doesn't exist, so at x equals 0, that's an asymptote. So asymptote at x equals 0, that's the y-axis, or the y-axis. So the y-axis is actually going to become an asymptote, regardless of what b is. That didn't matter here. So we've got that. There's really one more point, and that's going to make the difference now between these two graphs, because right now they look like they could be the same thing. What I want to look at here is what happens when y equals 1. So in other words, here's y equals 1, here's y equals 1. Let's solve for x. That would mean 1 equals log b of x. Again, we convert base to the exponent equals x. But any number to the first power is just that number. So x would equal b. Here's the difference. For b greater than 1, that means the base is somewhere out here. Let's just pick a random point. We'll call that b. It could be anywhere to the right of 1. If b is less than 1 but greater than 0, that means the base is somewhere in here. So let's just again choose something. It doesn't matter. What that's going to do is it's going to force the curve to go in a different direction. So when y was 1, in this case the base is beyond 1, so that would be a point up here somewhere. Since this is an asymptote, we have to go like this. So that's what the graph looks like. In this case, since b is less than 1, there's our point b1. It has to go this way if this is the asymptote. There's no other way it can go. So what happens here is the graph looks like this. And similar to the other, when b is greater than 1, we have an increasing situation. And when b is between 0 and 1, we have a decreasing graph. So these are differences depending on the base. If you recall, if you drew the line y equals x, the inverse graph mirrors the graph you're talking about. Well, the graph of y equals bx, where b is greater than 0, if you remember, it goes up like this. And it's asymptotic to the x-axis, so you can see they mirror each other around this line. Likewise, for this graph, a little more difficult to see, but this one is a decreasing graph, and it kind of looks like this. And if, hold on a minute, I got that a little too steep. So what we've got here, this is increasing. This is y equals bx. They're inverses of each other. They mirror each other. For y equals bx, but b is between 0 and 1, then we had the situation where it, again, was asymptotic to the x-axis, but instead of increasing was decreasing. So it went more like this. Let me see if I can get this sketched in here. Kind of looks like that. Okay, so that would be, and it's kind of hard to see, but they do look the same on either side of the line, like a scissor almost. So that's how they look. Another interesting thing, if you look at either graph, it doesn't matter about b, for the log, when we're talking about the domain, we can go anywhere beyond 0 out to infinity. So we're looking at something like this. And for the range of the log, it can go as high as you want or as low as you want. So we're covering all real numbers here. And if you recall, the domain and range for the for these graphs here, and you can kind of see it there, but if you just recall, for the exponential function, they were the opposite. For y equals b to the x, the domain in this case was negative infinity to infinity, and the range was 0 to infinity. And that's exactly how inverses work again. Their ranges and domains are swapped. Okay, So what I'd like to do now is one quick problem. And what we've got here is something we've done a lot. This is a problem where I would like to graph it, but what I need to do is start with the original graph and then apply the transformations. So this is just y equals ln x if you look at it. Okay, since this is ln, that means the base equals e, and e is roughly 2.7. So that means we've got the first graph I talked about on the previous page, where it's going to be increasing because the base is greater than 1. So we're somewhere out here. So there's our base comma 1 point. Here's our x-intercept. We know it's asymptotic to the y-axis, so again, I just drew this a minute ago. That's kind of our starting graph right there. So now all we got to do is apply the transforms and see what happens. Here we're going to go -1 in the x direction and -2 in the y direction. So we can start with these 2 points here. We had an x-intercept at x equals 1, y equals 0. But that's going to become a different kind of point. It won't be an intercept anymore, so we'll look at that in a minute. But where would this point go? X equals 1, but I'm moving left 1. Y equals 0, but I'm moving down 2. So if I calculate this out, we have the point 0 minus 2. So this point is going to go over to 0 and down to -2. So we have a new point there. Now we need to move the asymptote before we do much of anything. The asymptote was at x equals 0, or the y-axis, but x moves to the left 1, so our new asymptote moves to x equals -1. So we need to sketch that. Okay, so we know we've got something approaching this line and increasing, so we already got an idea what's happening here. Okay, what about this point? Well, that's the point B1. B, we're just going to use 2.7 because we have to estimate it. But then we have to apply these transforms, so we're going to go back 1, and for the 1 we're going to drop down 2. So where does that bring us? 1.7 minus 1. So go to 1.7, that's about here. Go to -1, that's here. So this point moves to here. Now I could go ahead and sketch this, but how do I get across the x-axis? It's a good idea to, since we lost our x-intercept, calculate a new x-intercept. That gives you a good point for sketching. So again, if I want to know where I am when I cross x, at that point y is 0. So put 0 into this original and see what we get. So y 0 equals ln x plus 1 minus 2. So what we're doing here is calculating an x-intercept for this function. All right, I need to get ln by itself before I can convert. So I'm going to add 2 to both sides. Now I can do the conversion. Base is e, exponent is 2, and the number is x plus 1. Now e squared is roughly a approximately 7.4. We'll use that. If I subtract 1 from both sides, my new x-intercept is 6.4, so go out to 6.4, okay? And that's where we're going to cross x. And you can see, if I didn't calculate that, I probably would have had a tendency to go up here. But what this thing's really doing is it's curving like this, and then it's going real flat here and coming through here, and there's the graph. Okay, and that's it. On part 3, we're going to do another graph type problem, but we're really going to look at domain and range there because of some things that happen, and we're going to solve an application problem.